do this problem using Ansys APDL. This problem, as you see, we have a rod that has two segments bounded by two rigid walls. The left side, the left segment is made of steel with modulus of elasticity of 29 million psi. The right side is made of aluminum with modulus elasticity of 10.4 times 10 to 6 psi, and thermal expansion coefficients are listed here. The segment AB, or the steel part, has the diameter, a circular section diameter of 2.14. The right side is aluminum, diameter is 1.5 inches. So knowing that the rod is initially under stress, we would like to find the stresses in portions A, B, and BC, and also we would like to see how much node B or point B is going to move. Is it going to move to the right or left, and finding the magnitude. Alright, so let's go to Ansys. By the way, solution is here. After thermal, after temperature rises, they're going to have compressive stresses forming on both rods. So in the steel, since it has a larger area, it's going to be smaller. It's going to be negative 5.25 KSI for the right side. The BC is going to be negative 11.82 KSI. And displacement of point B is also listed here. And it's going to go to the right. So this is the answer from theory. Let's model this in Ansys, see how we can model this. Alright, so let me drag this to the right. Alright, so we open Ansys APDL. Alright, so we're gonna do preferences. We're gonna do structural and thermal, and then preprocessor. I'm gonna pick element. Link element is gonna work here fine, so I'm gonna pick the link element. And then I'm gonna go here, material properties. We have a steel and aluminum, we need to define them. So for steel, structural, the modulus of elasticity was 29 million, so E6. And we need to have thermal expansion coefficient defined too. So let me show that. We have to go here. That one for the steel was 6.5 E negative 6 times 10 to negative 6. So I define that. Then I'm gonna go material number 2, which is my aluminum. I'm gonna do that one, modulus of elasticity is 10.4 E6, and thermal expansion coefficient is 13.3. It's like 2 times of what we have for steel. Alright, so we define those and now close it. Okay, so for sections, we have to define 2 sections. And for the steel cross-section area, the diameter is 2.25. So the radius is going to be 1.125. And then pi radius squared is going to give me 3.97608 for the steel. For the aluminum, section number 2, the area is going to be pi times the radius this time is 0.75 inches squared. I'm sorry, the radius is 0.75 inches. So pi times radius squared is going to give me 1.76715. All right, so sections defined. Now we have to model the rod. See, the steel part segment is 24 inches long, and after that we have 32 inches of aluminum. So we are going to define 3 key points. So key point 1 is 0, 0, 0. Key point 2 is located 24 to the right. Key point 3 is 56 to the right. I added the lengths of the aluminum and steel, so 56. So we have 3 key points. Now I'm going to create lines. Alright, so we did that. Now, next we need to, after modeling, we need to mesh it. So we have to assign the right mesh attributes to each line. So I'm going to pick this line, which is my steel one. I'm going to make sure we have material 1 and section number 1 assigned to it. And then I'm going to pick this second one. We got to make sure that material number 2 and section number 2 is assigned to that. Okay, next is mesh sizing. One element is sufficient here, so for all lines I'm going to assume just one element. And then since I have mesh attributes assigned already, I'm going to mesh all the lines. So we have them. Then okay, so loads analysis type is already, it's static, and define loads. Okay, so uniform temperature I'm going to apply to all of them. So 70 degrees was the elevated temperature, temperature rise. And we need to apply also structural boundary condition. So I go here, and the key point 1, we're gonna fix everything. Key point 2, also everything is fixed. So we did that, so everything is done. Temperature is defined too. So now let's see the solution. Solution done. And now let's look at the answer. Post processing. I go here. So list results. You gotta make sure that you read the last set of solution. Okay. And list results. Okay. First, I'm gonna look at the displacement. Nodal solution. Degree of freedom solution. The movement happens in the X direction. So let's look at that. Alright, as you see, node number 1, which was the steel connecting, the point that we had the steel connected to the wall, that was rigid. Displacement is 0. Point B, you see displacement is 0.0065 or 6.5 times 10 to negative 3. This is what we exactly had from the hand calculation. So let me show you 6.7, it's 6.57. Alright, so that is right. So, and then the right point also connected to the wall, doesn't move. Next, I would like to show you guys the solution. I'm sorry, the stresses. We could look, I see it under element. Yeah, we can see it under element. Sorry about that. Alright, so the stresses under element, the stresses in each element, you see that element 1, we have the stress negative 5252. So it's going to be 5.25 KSI, which is right. And then on the right side, right element at node 2 and node 3, we have stresses again in x direction, almost double, 11, negative 11.819, which is right. Both of them negative. So you see other stress elements are 0. So other stress elements are 0, which makes sense. Okay, so this is how we can do that. Oh, by the way, if you want to see reaction solutions, reaction forces are going to be the same, the wall supports. You see on left node, we have force 20.885 kilopound. This force is going to the right. Reaction coming from the wall, which makes sense because as this expands, wall A is gonna get pressed to the left, and wall is gonna resist against that. So that's why that force is positive. On the other side, at point C, cylinder is gonna press the wall to the right, and then wall is gonna react in opposite direction. It's going to be again, it's going to be this time negative. So, but they're going to be equal because you should have equilibrium satisfied. So that makes sense. All right, so I hope you guys find this short video useful.